Hello everyone, on behalf of Physics Made Easy Kota, I am welcoming you in our next video lecture. In this video lecture, we are going to study about the PN junction and its certain applications. So what is PN junction? PN junction is a single piece of semiconductor material which is formed when it is doped with the pentavalent impurity and also doped with the trivalent impurity. Then this semiconductor is known as the PN junction because now its one portion consists of the pentavalent impurity and the another portion consists of a trivalent impurity. The boundary dividing the two halves of such semiconductor is called as the junction. In the figure we can see that the holes and the free electrons are joined together to form the junction into a single form, and that single piece of a semiconductor is known as the PN junction. So for the formation of the PN junction, a small quantity of trivalent impurity is fused to the thin wafer. Wafer means a very thin slice of the N-type semiconductor. We can take the germanium or the silicon conductor. This process produces a P-type germanium just below the surface of contact. This P-type semiconductor along with the N-type semiconductor wafer form a PN junction. Similarly, we can make a PN junction by fusing a small quantity of pentavalent impurity into the P-type semiconductor. Then the PN junction can be obtained when P-type semiconductor is heated in phosphorus gas to result into diffused N-type layer on the semiconductor. For the PN junction, the two important processes are there. One is a diffusion, another is a drift that occur during the formation of the PN junction. The concentration of the holes is higher on the P side than on the N side of the PN junction. Similarly, the concentration of electrons is higher on the N side than on the P side of the PN junction. So, during the formation of the PN junction, the hose diffuses through the junction from high concentration region to the low concentration region, that is from the P side to the N side, so that combined with the electrons in the N region and they get neutralized there. Similarly, we can say that electrons also diffuse from the high concentration region to the low concentration region and combine with the holes. When holes diffuse through the junction, the P region near the junction is left with the negative ions which remain fixed in their position in the crystal structure. On the other hand, we can see when electrons diffuse through the junction, the N region near the junction is left with the positive ions and their position is fixed in the crystal lattice. Hence, the negative ions or receptor ions near the junction on the P side form negative charge region, whereas the positive ion near the junction on the N side form the positive charge region. This space region in which different kind of the charges are put together on the both sides of the PN junction called as the depletion layer. Semiconductor diode consists of the PN junction having metallic contacts at both the ends, and a cell or a battery can be connected across these metallic ends of the PN junction diode. So this figure represents the symbolic representation. The arrowhead represents the P-type semiconductor and the vertical line represents the N-type semiconductor. The arrow represents the direction of the conventional electric current through the diode. A PN junction is said to be forward biased or reverse biased. First of all, we are going to learn about what is forward biased. A PN junction is said to be forward biased when the positive terminal of a cell or a battery is connected to the P side and the negative terminal of the cell or a battery is connected to the N side of the junction diode. And we can see in the first figure that the positive terminal is connected to the P side, that is a whole side, and the negative terminal of the battery is connected to the N region of the PN diode. For the reversed biasing, PN junction is said to be reversed bias when the positive terminal of a cell or a battery is connected to the N side and the negative terminal of the cell or a battery is connected to the P side of the PN junction diode. In this case, the low current flows, whereas for the case of the forward biasing, a high or huge current is flowing. There are the various applications of the junction diode. Rectifier. Rectifier is one of the most important application. It is a device which convert alternating current into the direct current. So it based on the principle of the PN junction, that when a junction diode acts as a rectifier, it means that it start conducting when it is a forward biasing, and it never conduct or very low current is flowing when it is a reverse biasing. So semiconductor diode act as a valve, and this method is also known as a rectification, which means the process of converting AC into the DC. So for the rectification, which means for the conversion of AC into the DC, there are the two types of the rectifier used. This one is a half wave rectifier. So the rectifier which convert only one half of AC into DC is called as a half wave rectifier. In this figure, we can see that our AC signal, which is the input signal which need to be rectified, is fed to the primary coil of the transformer. The secondary coil is connected to the junction diode through the load resistance RL, and we get the output signal through the load resistance. So in this circuit, from the help of the half wave rectifier, we get the one half of the AC converted into the DC. So now to understand it properly, when the positive half of the AC input signal flows through the primary coil, it induces EMF in the secondary coil due to mutual induction. Let first case we consider the direction of the induced EMF is such that the upper end of the secondary coil become positive and the lower end of the secondary coil become negative, and we can see that the upper end of the coil is connected to the P region of the diode and the lower end of the coil is connected across the N region of the diode. So the positive get connected to the positive region, negative get connected to the negative region. So the junction behave as a forward bias, and during this only we get the output across the cycle. Now the current start flowing, the junction diode start conducting, and the current start flowing. Now we consider another case when the negative half cycle of the input AC signal is fed into the primary coil. Again EMF induced, and that is across the secondary coil due to the mutual induction. Now for this case, the direction of induced EMF is such that the upper end of the secondary coil become negative and the lower end of the coil become positive. Now the PN junction behave as a reversed bias because the negative end of the coil is connected to the P region and the positive end of the coil is connected to the N region. So for this case, the junction do not conduct, no current is flowing, and we get no output across the given input signal. So this is a wavefront, and we get output only for the half of the AC signal, and we get output only for that case when the PN diode is a forward bias and there is no junction current formation take place for the reverse biasing, and for that we get no output signal. Only the output signal is possible when the diode behave as a forward biased. As the efficiency of the half wave rectifier is less, so now we are going to understand how to improve the efficiency by using the full wave rectifier. So first of all, what is full wave rectifier? A rectifier which convert both the half of AC into DC, and we can see in the diagram that the AC input signal is fed into the primary coil of the transformer. The P region of both the diodes D1 and D2 are connected to into the secondary coil. The load resistance RL is connected between the common point of the both the diodes, and there is the output voltage obtained across the load resistance. So now first of all, for the working, when the positive cycle of the input signal flows through the primary coil, then again EMF induced in the secondary coil due to the phenomena of the mutual induction, and let the direction of the induced EMF is such that the upper end of the secondary coil become positive while the lower end become negative. Then you can observe that now which diode is a forward bias and which diode behave as a reversed bias. Yes, for this case, the diode D1 is act as a forward bias and the diode D2 is a reversed bias. So the current due to the diode D1 flow through the circuit in the direction and shown by the given arrow, and we get the output across the load resistance. So for the second half, when the negative half cycle of AC input is fed into the primary coil, then again the diode D1 and D2 show some changes. For this case, now the diode D1 act as a reverse bias and the diode D2 act as the forward bias, as the direction of the EMF get changed during the negative half cycle of the AC. So the current due to the diode D2 flows through the circuit and we get the output across the load resistance. So in this way it acts as a full wave rectifier. So we can see that since both the half of the input AC are available in the output in rectified form, so this is called as a full wave rectifier. We get the output for each diode, that for the first one for the diode D1, then for the diode D2, again for the diode D1, then again for the diode D2. In this way we get the full wave rectified, full conversion of AC into the DC, and in this case only the current flows when diodes behave like the forward bias. Firstly the diode D1 act as a forward bias, then the diode D2 in an individual case. So the output is continuous and efficiency is very high as compared to the half wave rectifier. Thank you for watching. Have a nice day. Take care.